Good morning. We have been discussing the inversion of the unilateral Laplace transform. Okay, and we have seen the inverse Laplace transform of the real poles, and we use the partial fraction expansion for the real poles. Now we'll discuss the partial fraction expansion procedure for the complex poles. We know that the complex pole usually results in complex value expansion coefficient, and therefore a complex exponential potential in time domain, and the suppose we have to find the inverse Laplace transform of this function, which is expanded by the partial fraction expansion with the complex poles, then this is accomplished by combining all the pairs of the complex conjugate poles into the quadratic terms with the real coefficients. Suppose there are alpha plus j omega naught and alpha minus j omega naught. This makes a pair of complex conjugate of each other. This makes a pair of complex conjugate of each other. So these are the complex poles, and therefore the first order terms associated with these two poles in the partial fraction expansion can be written as a1 over s minus alpha minus j omega naught plus a2 over s minus alpha plus j omega naught. So in order for this sum to represent the real value signal, a1 and a2 must be complex conjugate of each other. So this a1 and a2 must be complex conjugate of each other. Therefore, then and then we can replace these two terms with the single quadratic terms. The single quadratic terms we can write like this: if these two a1 and a2 are complex conjugate of each other, then this b1s plus b2 divided by this s minus alpha minus j omega naught divided by another term is there again, s minus alpha plus j omega naught. Okay, so this we can write also like this: b1s plus b2 divided by this. These are the complex conjugate to each other. Therefore, we can write this is s minus alpha square plus omega naught square. Okay, so where this b1 and b2 are the real value, and we then solve for b1 and b2 and factor the results into the sum of two quadratic terms, and therefore we can write the factor which is result into the two quadratic terms. Suppose we have to, this term is b1s plus b2. This term is there on the in the denominator, and therefore we have to write like this. Just for the simplification purpose, b1s minus b1 alpha plus b1 alpha plus b2. So we know that this b1s plus b2 term is there, and therefore this term, if you solve this, we will get the same equation, this equation. So further we can take here b1 outside the bracket, what will remain there, plus here b1 alpha plus b2, and this is divided by omega naught. So this we can write further by putting this value. This is just for the simplification purpose, b1s plus b2 divided by s minus alpha square plus omega naught square, and this is c1 into s minus alpha divided by s minus alpha square plus omega naught square plus c2 omega naught omega naught divided by the s minus alpha square omega naught square. So what is c1? C1 is here b1, where c1 is b1 here, and c2 is, what is c2? That is b1 alpha plus b2 by omega naught. And if you put these values, we will get the same equation, that is b1 of s plus b2. Okay. So this c1 is here b1. Okay. And this c2 is b1 alpha plus b2 and bracket by divided by the omega naught. Okay. So we can now take the inverse Laplace transform of these two terms, this first term and second terms. Taking inverse Laplace transform of the first term. Which one is the first term? This is the first term. So we have actually the inverse Laplace transform is like this: s minus alpha square plus omega naught square. So what will be its inverse Laplace transform? Okay, so this is actually the standard form of the Laplace transform. So constant c1 is here. Okay, then this is e raised to power alpha t into sine of omega naught t into u of t. So this is the inverse Laplace transform of the first term. Similarly, inverse Laplace transform of the second term. What is the second term? Second term is like this: c2 omega naught divided by this s minus alpha square plus omega naught square. So this constant c2 is again here, e raised to power alpha t, and this is actually this is the this is actually the standard form of the cosine term. C1 e raised to power alpha t cos of omega naught t into u of t, and this is omega naught by alpha minus s minus alpha square plus omega naught square. This is actually the sine, okay, sine of omega naught t into u of t. So this is the inverse Laplace transform of the second term, and therefore so what is the so we can write here first term is here C1 e raised to power alpha t cos of omega naught t u of t plus C2 into e raised to power alpha t into sine of omega naught t into u of t. So this is inverse Laplace transform of the given two quadratic poles. Sorry, complex poles. If the poles are complex, we already expand the function if the function is having the real poles, but if the function is having the quadratic poles, we can expand the function like this. And these things will be again clear when you consider one example. So example is find the inverse Laplace transform of x of s is equal to 4s square plus 6 divided by s cube plus s square minus 2. Okay, so there are three poles. Okay, why there are three poles? Because the order of this denominator polynomials are 3. So just trial and error methods, we have to find these poles. So this is s minus 1 and second is s square plus 2s plus 2 is equal to 0. So if you solve this, what will be there? S cube plus 2s square plus 2s, and again minus s square minus 2s minus 2 is equal to 0. So if you solve this, you will get the s cube 2s square minus 1s square plus s square. This is not there, and this is, so we will get the same equation. So these are the factors. Again, this is again the quadratic equation. And we have to again find the roots of this quadratic equation. So further we can find roots of the quadratic equation by using this equation minus b plus minus under root of b square minus 4ac by 2a. If you substitute the values from this equation, here a is equal to 1, b is equal to 2, and c is equal to 2, we will get the poles minus 1 plus minus j 1. So these are the complex conjugate poles. These are the complex conjugate poles. So we write this quadratic equation in terms of the perfect square. Okay, so perfect square means this is a s square 2s plus 2. Okay, we also write this s square plus 2s plus 1 plus 1. So this is the square of this term, s plus 1 square plus 1. Okay, so in this way we can also write in the perfect square term, and therefore the partial fraction expansion for x of s expansion take the form x of s is equal to a over s minus 1 plus b1 s plus b2 divided by the s plus 1 square plus 1. So this is a partial fraction expansion, and this is, we have replaced the above equation with the single quadratic terms, the second part of this equation. Okay, so the expansion coefficient a, this coefficient a can be found by the method of residues. So we'll first find the a by the method of residue. So s minus 1 x of s at s is equal to 1, and therefore s minus 1, what is x of s? X of s is 4s square plus 6 divided by this s minus 1 s square plus 2s plus 2 at s is equal to 1. Okay, so here these two terms will be cancelled. Now s is, we have to put s is equal to 1, so it is a 10, and this is again 1, 2 plus 2, so it is a 10 by 5, it is a 2. So value of a is 2 here. Now we have to find the coefficient a we have got. Now we have to find the coefficient b1 and b2. This coefficient b1 and b2 can be found. The remaining expansion coefficient b1 and b2 are obtained by placing both the terms on the right hand side of the expanded equation. So over the common denominator and equating the denominator of the results to the numerator, and therefore we can write 4s square plus 6 means we have to do, common the denominator from both the sides of this equation and equate the numerator of the results to the numerator of x of s. Okay, so equate the numerator of the both sides of this equation, and therefore it is a 2 into, after substituting the value of a1. We have substituted the values of is a1, and therefore s plus 1. Are you getting, or I will take one more terms? Okay, I will take one more step for simplification purpose. This is the s minus 1 s square plus 2s plus 2. Okay, and so we already find here the perfect square Therefore, we have to write here perfect square. It is a s plus 1 square plus 1. Okay. So the term on this side, what are the term on this side? It is a over s minus 1. So we have to s minus 1 is there, and therefore one more terms will be there, s plus 1 square plus 1. Okay, so we have to make the common denominator of the both the sides of this equation. So as we have multiplied by this factor in the denominator, we have to also multiply in the numerator. Plus, that is a b1 of s plus b2. What terms will be there? Here s plus 1 square plus 1. Okay, and one more term we have to add here, s minus 1, for making the common denominator. So here we have multiplied s minus 1. Here we have to also multiply the numerator by the s minus 1. Now we can say the equation has got the common denominator. Now we can equate the numerator of the both sides of this equation. So 4a square 6 is equal to a into a value we have got 2. So put value of a is 2 here. So 2 into s plus 1 square plus 1 plus b1 s plus b2 into s minus 1. Okay, so this term is there. Now we have to find the b1 and b2. So solve this further. 2 into this s square plus 2s plus 1 plus 1 plus this. Then we have to solve this b1 s square minus b1 s, this plus b2 s, and this is minus b2. Okay, so the terms will remain there. 2s square plus 4s plus what will be there? 4 plus okay, this 2 so this is there in the bracket. Okay, this is there in the bracket. So actually this total is s square plus 2s plus 2. So if you multiply 2, it will become 2s square 4s plus 4. This is b1 s square minus b1s plus b2 s minus b2. Okay, so it is b2, and what will remain there? S square terms are there. So this is a 2 s square. S square we have to take outside. So the in bracket it will remain 2 plus b1 into s square plus 4 minus 4 minus this 4 minus b1s plus b2s, and outside is 2. By taking these two 3 factors. So yes, terms 4 minus b1 plus b2 and this yes, plus these terms are remain 4 and minus b2. So 4 and minus b2. Now we can equate these two sides and we can find the values of. So this s square term we can equate. So 4 is equal to 2 plus b1, and therefore b1 is equal to 2. Similarly, we have to multiply the constant terms. There is no yes terms. Yes term is not there on the left hand side. Only constant is there, and constant is again compared with the constant. So this is 6 is equal to 4 minus b2, and this is minus 2 is equal to b2. So in this way we have found the this is b1 and this is b2. So we have got the values of b1 and b2. Now put this value in the equation. Therefore x of s is equal to value of a, we have got 2 upon s minus 1 plus b1s plus b2. b1 value is here. It is again we have got 2 value 2s minus 2 divided by the s plus 1 square plus 1. Okay. So again now here we have to, for simplification purpose, we have to again simplify this factor further. So this we can write 2 over s minus 1, and instead of this 2s minus 2 we can write here like this 2s minus 2. This we can write 2s minus 2 plus 2 and minus 2. Okay. So what we have added here 2 and subtracted 2. So there is no effect on the equation. Therefore we can write here 2 we can take outside s plus 1, and this is minus 4. So instead of this 2s minus 2 we can write these terms, the factor. So therefore plus 2 into s plus 1 over s plus 1 square plus 1 minus the second factor, second term 4 over s plus 1 square plus 1. Okay. Now this is in the standard form. This is in the standard form. What is the standard form? 2 over s minus 1 plus 2 into s plus 1 divided by s plus 1 square plus 1, and this 4 is here. We can write this for simplification purpose s plus 1 square plus 1. Now we can find the inverse Laplace transform of the equation. So what is the inverse Laplace transform of x of s? It is x of t on the left hand side. And what is the inverse Laplace of this term. So 2 is there, as negative sign is there, so there will be the positive e raised to power t into u of t. Plus, what is the inverse Laplace transform of this second term? Now this is the standard form. Okay, so what is the standard form? Now it is a cosine function. So 2 is already there, and this is the e raised to power minus t into cos of t into u of t. Okay, again this is again in the standard form. So minus 4 is there. Okay, and this is e raised to power minus t into sine of t into u of t. So this is the inverse Laplace transform of the given function which contains the complex poles. So in this way, we have seen how we have seen the theory how to expand the given function into the partial fraction which contain the complex poles. Thank you very much.